Hello and welcome to this introduction or tutorial for my Blender 3D star map add-on. With this add-on you can place stars in a Blender viewport based on scientific data. I made a short trailer for this add-on which should give you a brief overview over its features. The link is in the description. This add-on is primarily meant for people who are interested in astronomy and want to explore the stars and star constellations. But it can also be used to generate scientific graphics like this one here, which shows the motion of close stars within a time span of 100,000 years, or to generate maps of your favorite science fiction universe like Dune or Halo, as long as it is based on real stars. The maps here on this graphic, for example, serve as kind of a prototype for this add-on. The add-on is available on Gumroad. You'll also find a link to a free demo version in the description. Okay, so let's get started with the tutorial. I will go through each setting and explain and show what it does and how it can be useful. Timestamps are in the description. When you download the add-on, you'll get a zip file and you'll install it just like any other zip file in Blender. You go to Edit, Preferences, and here under Add-ons, you click on Install, select the add-on, and click Install Add-on, and there you go. You just have to tick the box, and then it's properly installed. Now that the add-on is properly installed, you'll find the add-on menu in the sidebar panel. So just press N, and here under Create, you'll find the menu. And I'm just going to give you a quick demonstration of what it does. I'll delete the default cube, click Preset World Settings, and leave all the default settings as they are, and click Generate Map. This will take a few seconds, and now we already have a bunch of stars in our 3D viewport. And if we go to Rendered View, you can see that each star also has an emission shader, so it's you're ready to render the scene if you want. Now, if you're using the default Blender theme, you probably have black star names here, which is not ideal because black names on black background means that you won't see the names in rendered view. So to change that, you can go to Edit Preferences, and here under Themes and 3D Viewport, change the option under Wire and Empty to a color of your choosing. And if you want, you can also create a new preset for that, so you can directly switch between your old default settings and star map settings if you want, like I did here with star map. Now, by default, the add-on will generate all the stars that are in its database within 100 light years of Earth. Now, the way this add-on works is when you install the zip file, you also installed a CSV file aside from the Python script. And the CSV file contains all the data that is needed to generate these maps. And the CSV file includes more than 3,750 stars. And of course, this list is not complete, but in the future I might add more stars to it. Now, by default, these stars here have relative sizes and luminosity, meaning that here by default the Sun has a size of 0.01, and if Aldebaran over here has a size of 0.441, it means that it is 40 times as large as the Sun in reality. So this is all represented here. Now, because space is so giant, the sizes of the stars are of course not relative to the distances between them here. It's just Blender is not made for such large numbers that it's basically impossible to implement this into Blender. So keep that in mind. The distances and the sizes of the stars are not relative to each other. But the size, aside from the size, the luminosity of the star is also relative. So if we go to our material settings here, you can see the emission of the Sun is 1 by default, and Aldebaran over there has an emission strength of 439, meaning that the luminosity of Aldebaran is 439 times as high as that of the Sun. And the color of the stars is also is determined by their surface temperature, which is the blackbody temperature of the star, and each star has the correct blackbody temperature as well. So you can see the Sun has an average surface temperature of 5,778, and Aldebaran is a bit colder with 3,900. If we now look at our outliner window over here, you can see the add-on automatically generated a few collections, and the stars also have the names as their in-scene name, and also the material has the name of the star. And you can see the collections are based on relevance. Each star has a relevance value that I assigned based on its importance, or rather relevance, and this is based on their primary name, the name which it is most known for, and there are different catalogs that determine the name, like the Bayer catalog. For example, if your star is called Delta Trianguli, like over here, then this is the Bayer designation, and it gets a relevance rating of 4, which is the highest catalog-based rating. Now, stars with 5 are Bayer catalog stars that have a proper name, and you can, for example, go to Wikipedia. There's a list of stars with proper names, and so Aldebaran has a relevance rating of 5, and stars with a Bayer designation as their most common used name have a relevance of 4. Now, for stars like 12 Persei over here, this is the Flamesteed designation, which I assigned to relevance 3, and other stars like other catalogs like HD or HR catalog get a relevance rating of 2, and relevance of 1 are like Gliese stars and other catalogs, and relevance of 0 are stars with very unpleasing to look at designations. So, and the basic rule is also that each star that has a proper name gets a +1 to its relevance. So, meaning that if a star that does not have a Bayer designation but a Flamesteed designation, but still has a proper name, then it gets a relevance rating of 4 instead of 5. Now I will go through each setting one by one and explain what it does. And you can also, I also made a documentation for this add-on, which you find as a PDF file in the description. If you want to get further details that I'm not gonna explain in all detail in this video, you can check this out, or if you rather read it, then you can also follow the link in the description. So the first setting here is preset world settings, and what this does is it just generates, it prepares the scene for you that you can easily view the stars it gives the scene a black background instead of the default gray one, and it also switches to Eevee and activates Bloom for easier viewing in the 3D viewport, and it also gives the stars a clamp value, which I'm going to explain later when we go to the actual clamp emission setting. And if you and further down, I will explain night sky mode, where it will automatically set up a camera as well for you. And it's just, if you want a quick scene and view the stars like that, you just click on this and everything will be set up. Now, disable stars in viewport. If I let's just restart the scene real quick, and if I click on that, you can see that stars are all disabled. It's basically, it does what it says, and this is useful for a number of reasons. First of all, it makes the generation of the map faster. But we have to enable them all one by one, like the collections one by one, if we want to see them in our viewport. And this, like Blender struggles a bit when a lot of objects are in the scene. Like with this add-on, you can add up to 3,750 or more than that stars, and this is a lot to generate. So this will make generation quicker. And also, if you're rendering your scene, you should disable all the collections if you have a lot of stars, because like the actual render of these stars does not take very long, but it has to prepare the scene and go through each object before rendering, and this might take like 10 times as long as the actual render. So you want to make sure that if you have many stars in your scene and you're doing a render, that you disable all the collections first. Now here under size, you can determine the size of the sun. So I said earlier that the sun has a size of 0.001 in this 0.01 in this default settings, which is exactly the number here. And the stars will be relative to that. The other stars will be relative to that. So you can also set the luminosity here, which is the emissive strength of the sun. So this is this value, and the other stars by default will all be relative to that. So but you can also make them all uniform, so they all have the same size or the same luminosity if you want. This is hidden under advanced options, because I didn't want to overload you with a large menu with options that you might not even need if you're doing a basic scene. I hid them away under this option. If you click on advanced option, you can see there are a bunch of more options, and there's also uniform star size and uniform luminosity. And I'm just going to restart the scene, and now if we click on uniform star size and set this to something like 0.1, you can see each star has a size of 0.1 instead of the relative size that they have by default. And here's also the option to hide all stars in render. It basically just disables the render button on all collections. Now, there's the next setting is the subdivision setting. The sun by default has a subdivision surface modifier, but you can see if I'm just gonna disable uniform star size and regenerate the map, you can see that Aldebaran is a lot larger than. We should probably set the size back to 0.01. And you can see that Aldebaran is, because it's larger, it gets automatically a subdivision surface modifier, so that larger stars look better than smaller stars, which you might not actually see in your render that well. So here you can determine at which size of the star relative to the sun it will receive a subdivision surface modifier. So if I set it to 5, all stars that are 5 times as big as the sun will get a subdivision surface modifier. The sun will also always get a subdivision surface modifier. So the next setting, clamp emission strength, that's what I said earlier here. Under Bloom, there's a clamp value that's automatically assigned. Now it does that because if we generate a default map, then you can see that some stars are, of course, if they are bigger and have a higher luminosity value, they look a lot brighter. Now this doesn't cause any major issues here with stars within 100 light years, but if, for example, I'll get to that option later, if I add Betelgeuse and to our scene, you can see that here it's with a clamp of 10, it looks okay, but if I disable that clamp, it overloads the entire scene because the luminosity of the star is so high that it overloads the scene. And to prevent that from happening, I set this by default to 10, so you can view it in the viewport. But this option here causes a bunch of problems. You can see Betelgeuse over here has a rather white color, and if we decrease the surface temperature, like if we go to 2000, then you can see it's green, and stars are not green. So that's an error with the Bloom clamp of Blender. And here under clamp emission strength, we can directly set it for the emission strength. So if I delete this and set this to 10 and generate it again, you can see the star here, Betelgeuse, has a strength of 10 instead of the large number it had before, and it has the correct color, which is this orange color. And if we go down in color, you can see it's more red and it doesn't turn green. You might have noticed if I set this to something other than 0, it will disable the clamp here in the EV settings. So the next setting is use proper names. As I explained, some stars have proper names. You can check out a list on Wikipedia for that. And if you don't want any proper names in your scene, you can just let me set these back to default. You can disable this, and then you can see that for example, here Alpha Tauri is actually Aldebaran, but it will show up as Alpha Tauri here now. So here you can control how you want them displayed. So moving on, show system composition. If you enable this, which is enabled by default, you can see that some stars have these letters in their brackets, which which basically says that this star represents multiple stars. So it's a binary or trinary system. Unfortunately, it's because, like I explained, space is very large and the stars are relatively small compared to the vastness of space. I'm not really able to properly display binary systems with two separate objects in Blender, because if I would here Alpha Canis Majoris, which is Sirius, if I would add Sirius 1 and Sirius B to the scene, Sirius A would be much larger, and because Sirius B is like very close to Sirius A, it would just be inside the sphere of Sirius A. So or they would overlap and you wouldn't see a difference. So what I chose to do is the brightest star of each system is basically the star that represents the entire system in this. So this the star here is just Sirius A with its settings here, but because there's AB in the bracket, it represents Sirius A and B. And if you want to disable this these brackets in viewport, then you can disable this here and generate the map. And as you see, now it just says Sirius, and because we also enabled proper names again, it will show up as Sirius instead of Alpha Canis Majoris. So next we have the option to set galactic coordinates, and galactic coordinates means that the north is the northern like the north coordinates of our Milky Way, and now I'm not sure which direction is the center, but I'll just add the black hole in the center of our galaxy really quick. And here you can see here's the center of the galaxy, which is, I think, along the x-axis. Yes, it's positive x-axis, and the anti-center will be in this direction. So that's galactic coordinates. And if you disable this, it will use celestial coordinates, meaning that the North Star, Polaris, will be at the top coordinate of the coordinate system, and it will represent the night sky. Oh, I have to disable this and set this back to 100, and there we go. Now you can see that like Polaris is not within 100 light years, but Ursae Minoris, which is the star constellation where also Polaris is a part of, is at the top, and yeah, it's celestial coordinates. So let's take a look at the filters, and there are multiple filters in this add-on which allow you to limit the amount of stars that are displayed in a scene based on certain parameters. First, there is the distance filter, which lets you set the minimum and maximum distance from Earth a star can have to be displayed. So by default, it's 100, and you get all the stars within 100 light years. But you can also set this to an in-between value, like from 50 to 60 light years. Then you would get all the stars that are 50 to 60 light years away from Earth. And to get all the stars, the furthest star in my CSV data file is billions of light years away. So you would have to set this to a very high number, like 10 to the power of 16, and then you would be able to generate all the stars that are in the CSV file. Now, as you can see, you get a warning message up at the top here, which should give you a rough idea whether it might take a bit longer to calculate the stars. The computation time for all the stars on my computer is about 3 minutes. It might this might vary depending on your processor, and but it's for most settings here it's not too long. If it appears that Blender might crash when you click Generate Map, just wait a few minutes. Even if it's stuck, it should actually finish, and you just wait. So if we go to advanced options, you can see there are multiple other filters. And first there's the inaccuracies allowed filter. And when I gathered the data for all the stars, I was unable to find data regarding some of these stars, mainly their radius, their luminosity, and the temperature was not always given. So I introduced a setting which lets you filter out values that I had to calculate based on existing data or that I had to guess. So if two of these values, if for example a radius and luminosity were given, it's quite easy to calculate the temperature with the Stefan-Boltzmann law, or there are also other formulas that can calculate certain parameters, but and these values are usually quite accurate. So if you don't want any calculation or guesses, set this to 0, then you get just the stars that have known radii, luminosities, and temperatures that I was able to find. So if you set this to 1, you'll still get if I calculate one missing value, and if I calculate 2 missing values, then of course the error gets bigger and the results might not actually represent reality anymore. So 3 is the maximum. With 3 you get all the stars, no matter whether I had to calculate or guess the value. You can read more about this in the PDF documentation file as well. Next is the apparent magnitude. Here you can filter out the stars based on, well, apparent magnitude, and it goes from minus 26.7, which is the apparent magnitude of the Sun, and up to 30, which is the highest value you can set here. And this value 30 also includes all stars where I could not find any apparent magnitude values, which are only like a handful of stars, but still. So if you don't want them, you can set this to a number lower than that. And relevance filter, which is also shown if you disable advanced options, is basically filtering here based on these collections. So if I only want the most important stars with relevance 5, I can set this to 5, and there we only have 5 relevant stars, and the other ones are not generated. And display names just is also relevance based, and here you can set which stars should display the name in viewport. So if I set this to 0, so we generate all the stars within 100 light years, and set this to 5, then you can see it will generate all the stars, and but only the relevance 5 stars show their names. So if I select all, you can see there are other stars and their names are not shown. And if you set this to 6, you won't see any names in the viewport anymore. So when I enable advanced options, you saw the setting earlier, I have a text, like a text box here, where I can search for specific stars. So for example, if I want just Sirius, then I have to set the filters up as well. So if I set this to like 5 light years, then we won't get anything. We have to make sure that it's within the given other parameters. And I set this to Sirius, and then as you can see, I have to switch display names back to 5. As you can see, we get just Sirius here. And this works also for the non-proper name. So if I type in Alpha Canis Majoris and delete Sirius, and you can see it still generates this. And this works also if we disable this, and vice versa. Just make sure you get the capital letters right, and because otherwise it won't find the star. And you can also type in like parts of the name. If you type in Kepler, for example, and set this to high number, and you would get all the stars that were discovered with the Kepler telescope, for example. Next are the spectral class filters. Each star has a spectral class, and which is roughly based on its surface temperature or its properties. And these are the main sequence stars, which Sun, for example, is a G-class star, and K and M type stars are usually colder than the Sun, and O, B, A, and F are hotter than the Sun. So here you can filter out certain spectral classes. If I disable these here as well and select G, then we get all the G-type stars that are in the same spectral class as the Sun within 100 light years. And I can also do this for brown dwarfs, which are outside of the main sequence, and other stars like carbon stars or even black holes and other things. Now, if I check advanced options, you can see there are additional objects. These are placed, these are not stars, these are like galaxies or nebulae, and are not represented by an icosphere like all the other stars. They are just an empty object. And if I generate them, then you can see we get here like galactic North Pole, South Pole, and galactic centers somewhere, and certain nebula and galaxies like here the small Magellanic Cloud. Now we get to the additional settings and features in this add-on, mainly stellar motion, night sky modes, and star constellations. And first, stellar motion. With stellar motion, you can animate the stars over time. Each star has a proper motion and radial velocity. The proper motion is the movement on the night sky, and the radial velocity is if the speed at which the star gets closer to Earth or moves further away from Earth. And I use these values to calculate the velocities of each star in 3D space. And here you can set the start year and the end year of the animation, and the first frame and the last frame. And if we the current year is the start year, so you don't type in 2020, you just type in 0, and end year is here in this case 100,000 years into the future. So if I now generate this map, we get all the stars within 100 light years and at the current moment in the current year. And if we now press play, you can see the stars are moving like they would within the next 100,000 years. In this case, over 10 seconds. So the movement that I calculate here based on proper motion and radial velocity is linear. Now this is just an approximation, because if a star is influenced by gravity, for example, through another star, then its path might change and no longer be linear. So keep in mind, this is just an approximation, and the further away we go from today, the more inaccurate, of course, it gets. And you can also set the start year or the end year, so the time frame to the past. If I type in 100,000, for example, negative value, and the end year to 0, then I can generate the map, and you can see that the stars are now. You can see now how the stars were moving from 100,000 years ago to today. And when I select advanced option, you can see we have an additional setting here, which you can use. If you enable this, it will not use the current year for this distance filter, but the start year selected here. So if I keep it like this and generate the map, you would get all the stars that were within 100 light years 100,000 years ago. Next is night sky mode. Night sky mode is a mode where the stars are all projected onto the surface of a sphere, so they won't have their coordinates in 3D space like they would normally. And if I generate this real quickly, you can see it. They are all on the surface of a sphere. The radius of the sphere is determined by this value here. Now we can see if I select preset world settings, it will automatically set up a camera at the center. And here's the sphere. They are all 100 light years away, or 100 blender units rather, away from our camera. So I made this to let you view the night sky, and because of that, like, the stars have to. When we look at the stars, they appear all the same size, almost infinitely small. And if I would disable this, then of course, a star that's 1,000 light years away would be smaller than a star that is 10 light years away, just because of the way distance works in Blender, and I can't represent like actual light year distances in Blender. So yeah, and it will also use the apparent magnitude for the emission strength instead of the luminosity, which might be different from the luminosity in some cases when stars are blocked by certain when the light is blocked by something or on its way to Earth. So they might appear actually fainter than they are than one would expect based on the luminosity sometimes. So what my recommended settings for night sky mode are uniform star size. Of course, you want the stars to be all the same size because they will appear from Earth the same size, and I think a size of 0.005 is a good size to so they don't appear too small if you use 100 Lambda units as the radius of the sphere. And you can also select variable stars. Some stars change their luminosity over time, and this will animate the magnitude value, and it will generate a random point in between the minimum and the maximum apparent magnitude, and from there it will go to the maximum or the minimum, and then to the other one, and over the given time frame here. Now variable stars have different maximum minimum periods, and this is not unfortunately represented here because there's not a lot of data about the time spans at which they reach minimum and maximum. So I chose to make the time, like the time of the it takes from minimum to maximum the same time for all stars here. So keep that in mind. One thing to note, what I forgot in stellar motion, is that I couldn't find data for some stars regarding their proper motion and radial velocity. And if you select stellar motion, some stars are just filtered out and not displayed anymore. This brings me to my next point, which is stellar motion in night sky mode. You can select both night sky mode and stellar motion if you want, and this way so what changes is that now the movement can no longer be linear of the stars, and 2 keyframes are not enough to animate them because they are moving on the surface of a sphere now. So this takes longer to compute, and because of this, I set up a step size. Now, ideally, if you want accurate results, you want a keyframe at each frame, but this takes so long that if I set my distance to maximum, if I would get all stars with a step size of 1, then it doesn't finish on my computer. So I set up the step size, and here you can set the number of frames at which keyframes are generated. So at 5, each fifth frame, a keyframe will be generated. So I'm gonna just use a very small number so it doesn't take as long. And I can set this to 1 because these are not very many stars. Okay, so now you can see, and I probably should have changed the display names to 0. And now you can see these stars, which are within 10 light years of Earth, are now projected on a sphere. And if I press play, they are moving on the surface of the sphere. As you can see, if the stars get closer to Earth, they move faster on the surface of the sphere. Of course, because they are closer to Earth. And for example, Barnard's star here is accelerating and then slowing down when it gets further away from Earth. And I'd recommend, if you have many stars that you want to animate, for example, the whole night sky with over time, that you use a step size of 1 for the closest stars and then move to 5 or a higher value for stars that are further away, because then the inaccuracies won't be noticeable if you view them from the camera in the center. And as you can see, if I select here Barnard star, you can see there's a keyframe on every single frame. Now moving on, the last feature is the star constellation feature. Now I'm going to disable night sky and stellar motion mode, and here you can see if I click add star constellations, I also have multiple options. I can this will generate this will connect stars based on the IAU star constellations, and this feature will automatically generate the stars that are needed and will connect them. So if the stars are already in your scene, if you, let's say you generated here all the stars that are available in my add-on, and then press add star constellations, it will search if the star is already there, and if it's there, it will connect them. If it's not there, it will generate it anyways. So if I set the distance here to 0, we shouldn't get any stars. If we remove that and generate, you see nothing happens. And if I click add star constellations, it will generate all the stars that are part of a star constellation. Okay, now it has finished. It took a bit less than a minute, and you can see here these lines are the star constellations. Now, of course, star constellations only make sense if we view them from Earth. So if we go closer here to the center, you can actually see the constellations. Here's Orion, here's Gemini, and so on. And if you move out, you can actually see how the star constellations would look if you would view our galaxy from the top. So there are also a lot of settings here. You can set the line size, which is the these are curves. So it's just the where is it, the bevel depth of each constellations, and the luminosity is the emission strength of the material. And you can, by default, it will generate a random color based on a seed for each constellation, but you can also disable this, and it will generate one material for all constellations, and you can then set the color when it's generated. Now, if I click show constellation names, then it will display the names of the constellation in the viewport. If I click show star names, it will display the names of all the stars that are part of the constellation. You can see that that it moves here closer to Earth when it gets to Alpha Centauri, and the constellations generated this way are of course then distorted. But if you generate the map with night sky mode, then they will all be on the surface of the night sky mode sphere. Okay, so I just press generate map, and then you will see disable variable stars, and then you will see what happens. Okay, it has finished. So now we can see it set up a camera at the center of our scene, and if we move the camera, we can see the undistorted star constellations, and if we move out, you can see all the constellations are on the surface of a sphere. Now, you might have noticed that if you click star constellation, stellar motion disappears. Unfortunately, I didn't set it up so you could run it directly with stellar motion. So there's an option, there's kind of a workaround for this, where you can still see how star constellations looked at a certain point in time. So to do this, you would have to generate the stars first and then add the star constellations, because like I said, star constellations search for if stars are already there that it needs, and if not, they will generate them. The generation is not influenced by the stellar motion. So you would have to, let's delete all of that, and now we can set up our parameters so that we filter out all the stars that are definitely not part of the constellations. And to do this, we set the maximum distance to 13,000, because the furthest star that is part of a constellation is a bit less than 13,000 light years away, and we set apparent magnitude to 6, because the faintest star that is part of a constellation has an apparent magnitude of slightly below 6. So, and then we are almost done. We just have to set up the stellar motion parameters. We want to know how the star constellations looked 100,000 years ago, and we make sure that start year and end year is the same, and we set the first frame and the last frame, the first frame to 0 and the last frame to 1, because we don't want to generate keyframes for our entire timeline, and this would take too long, and we set the step size to 1. And now if we generate the map, this will take a few minutes. We also disable stars and viewport, so it's faster, and we can then add the star constellations on top of that. Okay, so it has finished, and you can see here in the outliner we have all the stars there. And if we now move to add star constellations and set the max distance to 0, so we don't generate any additional stars or duplicates, and then we can generate the map, which shouldn't take too long. And there you go. You can see all the star constellations and how they would look like in 100,000 years, or rather in 100,000 years ago. So we can see here Orion's bow is very distorted, and if we go to Gemini here, Pollux over here has moved to the top and gave one of these twins a long head, and so on. So this is kind of the workaround for star constellations in the future or in the past. And you can see here a line goes through the sphere. That's because the star has moved so far away that it can't possibly connect it on the surface of the sphere anymore. It's just the way it is. Yeah, so that's basically everything I wanted to cover. If you are interested in further details like the sources for all this information and or other details, you can check out the PDF documentation in the description. And I hope you are having as much fun with this add-on as I have. And yeah, that's basically it. Thanks for watching.